Now, from equations 1 and 2, we're gonna get this equation, and we can take a common term here out of this equation, leave this bracket alone. So we end up with IC1 equal to such and such, and IC2 equal to such and such. IC1 is given by equation 3, and IC2 is given by equation 4. And both currents are shown in this figure. And they are drawn in a normalized way. We normalize IC1 and IC2 with respect to IO. With respect to IO. In other words, if you divide IC1 by IO, it gives you IC1 as a percentage or as a fraction of IO. That's called the normalized value of IC1 or a normalized value of IC2. So we expect the maximum value, the normalized value, to be 1. IC2 over IO, the maximum is 1. And IC1 over IO, the maximum is 1. The two curves are like this. And there is a 0 in the middle when the two input voltages are equal. When these two voltages are equal, you should expect this point, VB1 minus VB2 divided by V thermal. The input voltages are also normalized with respect to V thermal. And at that point, you get 0.5, which means 50% of the tail current goes each way. The current is exponential. The exponential becomes almost a straight line in the middle here, almost. And then it levels off, reaches some kind of a saturation here. I'm saying almost because you need to know that it's not 100% straight line. It's not direct proportionality 100%. You could say it's a straight line 99% maybe, or 98%. That's not 100%, because originally these lines are exponentials. You see? These are exponentials here. So these are hyperbolic functions, we call them. When you have a function full of exponentials, it's called a hyperbolic function. If there is no sine or cosine, if there is a sine or cosine and the imaginary term I, that becomes a trigonometric function. But if it's only exponentials with no complex variable I, which is the square root of minus 1, that's called a hyperbolic function. All right, so that's the picture. There is an area here, that's what we should emphasize. There is an area here in the middle where you have a almost straight line performance. This area in the middle here. And the straight line we can approximate this by a small signal model, by the way. When you have a linear response, we can approximate this region by a small signal model. Maybe someone in the EE 330 course has told you that already. As a matter of fact, the derivation of the small signal model, when you have a small signal model, you use it only when there is a linear performance. Well, that's not linear 100%, but we can make a good approximation and say, okay, this is almost linear. So we're gonna apply the small signal approximation. It's based on a Taylor series expansion, and we truncate it after the first order term. We neglect second and higher order terms. If you retain only the first order term, that becomes a first order approximation, and you take the linear part, and that's how we deduce the small signal model. They do that in 330, by the way. Let me give you the overall picture of these amplifiers. The amplifier, we work with two gains. One of the gains, okay, this example will illustrate the fact that there is something called the differential gain and something called the common mode gain. That's a differential amplifier. The differential amplifier example here, we have a single output. By the way, that's slightly different from this one because we have a differential amplifier here, but we have two outputs. You can take a single output and ignore the other, so you will end up with the same situation. The op amp is a differential amplifier, by the way. Yeah. Let's have two scenarios here when you have an input voltage of 101 microvolt, another of 99 microvolts. The difference between the two is 2 microvolt. Let's take another example. If this is 1 microvolt and this is minus 1 microvolt, the difference between the two is 2 microvolts. So someone from the outset might think that these two scenarios are identical. In fact, they are not identical. Although the difference of potential between the inputs here is the same as the difference of potential between the inputs here, but these two situations are not identical. Why? Because there is another term that we're gonna study that's gonna come into play here for the first time. That's called the common mode component. The common mode voltage. What is the common mode voltage? It is the average of these two voltages. It's the average of these two voltages. It's called the common mode voltage. So the common mode voltage in this case is 0, but the common mode voltage in this case is 100 microvolt. Believe it or not, that common mode voltage could give you totally different results. Although the differential component is the same, and we're talking about the subject of differential amplifiers. So somebody may think that the common mode component is a trivial thing. No.